So is my screen visible?
Yes, it's visible now. Yeah.
Okay, okay, okay. So, yesterday we were seeing quantum phase estimation with Qiskit. We saw the quantum circuit for quantum phase estimation. We also saw that where first we apply Hadamard gates and then we apply controlled unitary operations. And after that, we apply the QFT dagger, which is the inverse quantum Fourier transform, which you have learned last week. And then we apply measurement to check the phase value which has been estimated by the circuit and which is stored in the first register. So this is the circuit, as you all are familiar with this. This is the same circuit which we saw yesterday. And also, as you know that this is used to extract the eigenvalue of an operator, and it will be used as a subroutine in Shor's algorithm. So we are going to see that also. So these are just two diagrams to to reaffirm those facts. Now again, we import the necessary libraries. We create the function of inverse quantum Fourier transform. So this function comes from last week, where first you apply the swap gates and then you apply the control phasing gates and then lastly Hadamard gates. So basically, inverse QFT is the opposite circuit, basically the adjoint circuit or the inverse circuit of the quantum Fourier transform, right? In quantum Fourier transform, what happens? We have studied last week. We apply the Hadamard gate, then the control phasing gates, and then lastly the swap gates. Because the swap gates will be applied, right? In order to reverse, because the expression mathematically which you appeared was reverse of that the original QFT, right? Therefore, you have to reverse using the swap gates, right? That was explained by Muhammad Amir last week. So because of that, so therefore we start in opposite way. We first apply swap, then control phasing, then Hadamard. So we go in opposite way, and that is the function for QFT. So once you go through QFT again, this will become much more clear. And then what we do is that we make the function for QPE. So what will it do? QPE will have both the registers, right? First register, second register. So that means control qubits and target qubits. So second register is the target qubits, control qubits is the first register, right? And it will take the circuit and the angle, right? It will take the angle which is defined in the operator. So for example, if you take the S gate has the angle of, what is the angle? E to the power I pi by 2, right? That is the angle of the S gate. So therefore that angle it will take. So angle, what is the angle which is attached with I? The angle is what? Attached with the I, the complex coefficient, the complex symbol I. Whatever value attached with that is the angle. Therefore, now what happens is now that we will start with the repetitions one, because remember we have to repeatedly apply controlled unitary, and controlled unitary means nothing but control phasing gate. We have to apply control phasing gate according to the angle. So control phasing gate will take the angle, because according to this angle the first register will store the value, right? First register is going to store the value. We have learned this in theory yesterday. And then we will have the control qubit and the target qubit. So control phasing will be applied according to this angle from the control qubit to the target qubit, because remember from the target qubit then phase kickback happens and it goes and it rotates the control qubits in the first register, and then it stores the value in an accumulated manner. So for that we take the loop up to target qubits, up to the number of target qubits, because from the target only we are going to rotate the first qubit, and another loop for the repetitions, that how many times we are going to apply the repetitions. Okay, and we keep increasing the repetitions by 2. Now remember, this is the example which I was explaining to you today. So yesterday I gave you a small example of T gate. So T is the unitary operator, and then we applied we saw that how we can calculate the theta value. So if you do that calculation for the S, therefore when we give the angle as pi by 2, if you recall, S has e to the power I pi by 2, T has e to the power I pi by 4. Whatever attached with I is the value, is the angle, right? So if we give that pi by 2, the estimated theta which should be in the first register of the QPE circuit should be 1 by 4. We should receive theta is equal to 1 by 4. So then we start our circuit, we define our angle, very simple. We define our quantum circuit 4 comma 3. Why? Because there will be 3. We are going to only measure the first register, not the second one, right? We have seen this in theory. And even in the above diagram also you saw that we are only going to measure the first register, similar to Deutsch, Jodza and all those algorithms. Then we apply Hadamard gate according to the circuit counting register. First register qubits we will apply Hadamard gate, right? And then we initialize the second register to 1. So this is our eigenvector. If you remember ket psi, as I have explained you, ket psi. So here it becomes 1. That means a flipped. And then we apply the QPE function. Okay, QPE, which is our circuit, QPE main. We call this function, we give the angle, we give the circuit QP, and we also give the qubits. Now, then we apply the inverse QFT. So the code is very simple. If you can see, it is very, very straightforward and simple. We are just going step by step of whatever we did. 1, 2, 3, 4 steps we are doing. And finally, we measure it in the end and we draw. So this is how the circuit looks like. So if you can see in this middle part, so this part of the barrier, so I have put it in barriers. If you see here, we have Hadamards, then we put a barrier and then we define our ket psi basically, which is the second register. Ket psi stored in second register, right? And then this middle part is the part of controlled unitary. So this is a controlled unitary, this is a controlled unitary, as you can see. Okay, so this is the first controlled unitary, and these two operations repetitions are the second control unitary, then this is the third control unitary, and so on. So this is how all the unitaries are being implemented. Okay, so they keep on applying with this order. So this is applied. Okay, and then this one is applied. So if you can see, this is like u2 to the 2 to the 1, this is like u2 to the 0, and this is u2 to the square. 2 square means 4, so 4 times CP is applied, as you can see. So this is how we are applying. Actually, if you remember, we were going like u2 to the n minus 1, n minus 2, up to 2 to the 0, right? So it's a similar format, only we are applying here. U2 to the 0, u2 to the 1, u2 to the 2, and then u2 to the 3 will be what? 8 times. 8 times control phasing will be applied. Then 2 to the 4 is 16. 16 times it will be applied, right? So in that format, these are applied. And then this is the inverse quantum Fourier transform, right? We start with the swap gates, and then we will have Hadamard and CP gates accordingly. And finally, we take the measurement. So the circuit makes sense. Circuit is easy to understand. Just remember how this control phasing is being done, how the controlled unitary is being applied. It is applied that much number of times, that means that much number of repetitions according to u2 to the 1, 2 to the 2, etc., according to that value. And once you do that, then this code is the same from the previous one. So you can just take this binary value directly and start calculating. Since we have taken care of the repetitions and ordering, so therefore we can directly take this. We have obtained the value. We obtained the 010 binary, which if you calculate becomes 2 in decimal, and therefore the solution is solution divided by 2 to the n, and therefore 2 divided by 2 to the 3. Why? 2 to the n. N is what? If you recall, n is the number of qubits in the first register. How many qubits do we have in first register? 3, right? We have 3 because only the first register is measured. If you recall, only first register is measured, and we have 3 indeed. Therefore, the first register has 3 qubits, and the last register of single qubit, which holds the eigenstate ket psi, right, which is ket 1 in our case. Therefore, we apply that solution, and 2 divided by 2 to the 3 is indeed 1 by 4. And what was our expected theta? Theta should be is equal to, we obtain theta is equal to 1 by 4, and indeed by calculation you can see we indeed obtain the expected theta. So therefore, by giving the angle which is associated with the quantum state, so for S gate it is EI pi by 2. Now I would say that you also apply this for T gate as well. You will be able to find that the value is indeed 1 by 8. You should also do that exercise. but also you can do it with a generalized theta. So let's say if you have a unitary, this is some gate which has e 2 pi I by 5. Therefore, angle is 2 pi by 5, right? Whatever associated with I, that is the angle. Now, you can do this in this format. So therefore, the now this code will be for a general one. So in this, we define our control qubits. You can take the number of control qubits according to the precision you want to obtain, right? If you remember. So that is why now what we are going to do, we are going to take the control qubits as eight qubits to have precision of 1,000, because remember, like, in the binary 1 by 5, like five number itself is represented using three binaries, right? So therefore, according to that logic, we have defined the control qubits to be 8. That means the first register has 8, so like that. And then rest of the circuit remains the same. So we apply Hadamard's, we initialize a circuit, and then we apply the QP function. We initialize the second register to eigenvector eigenstate 1. And once we do, then you can see, now this time you can see u2 to the 0. If you can see, this is the, if you can notice my arrow, this is u2 to the 0. This is u2 to the 1. 2 to the 1 is 2, right? Therefore 2 times u2 square, as you can see, 2 square is 4, right? So 4 times CP, as you can see, repetitions. And then look at this, u2 to the 3. This will be 8 times. Look at this. 1, 2, 3, 4 here and below. Look at this circuit is very large. Here 1, 2, 3, 4. Then this is u2 to the 3, right? Then u2 to the 4. That means 16 times. So here you can count 1, 2, 3, 4, 5, 6, 7, 8. This is 8. Okay. And this is again 8. Okay, look at my arrow. This is again 8. This is u2 to the 4. So as can you see how the CP is being repeated that much number of times? So what is the meaning of the repetition? You already know, and we have studied this yesterday in theory, that the number of repetitions you apply turns due to phase kickback. It turns, it rotates the first qubit registers accordingly and stores the phase value. So this is what it is doing actually. And this is u2 to the 2 to the 5. That means 32 times. Okay, this is 32 times, as you can see. Then u2 to the 6. Okay, then u2 to the 7, it has come, right? 2 to the 7, this is, as you can see, is quite a large one, right? Quite a large circuit. u2 to the 7. Okay, it's going on. Okay, and then after that you have the inverse QFT. Okay, with the swap gates and then Hadamard CP, Hadamard CP. Okay, so this is a large inverse QFT circuit as well, and after that you take the measurement. Okay, so no need to be afraid of the circuit because this is created by Qiskit. The only thing, as you have understood, is the algorithm. That's it. Algorithm is very simple. As you can see, it utilizes inverse QFT, and we just need how many repetitions we need to do. That's it. And then this code is same. So therefore we achieve the total counts. We plot the histogram for all the counts, and we see that for this value 00110010, this binary value, we have achieved higher probability 0.87. That means 87%. Okay, therefore we take that, and the solution is 50 decimal divided by 2 to the n. Therefore 50 divided by 2 to the 8, right? Because the first register has 8 qubits, right? As we have defined in our code. Therefore 50 divided by 256 is 0.195, which is approximately zero point 0.2. Okay, and the expected theta was 1 by 5, which is also zero point 0.2. Therefore approximately with higher, much where with the higher probability, we have achieved our expected theta. So therefore, as you can see, we are able to achieve our theta value in this format. And as you can see, this is a generalizable code. So now you can utilize this code to estimate some other values of theta and play around with this tutorial to gain much more knowledge. So with this, now we conclude QPE, and the code is very straightforward. The only thing which you need to remember, is the inverse QFT, which we have studied previously, and the function to compute QPE. That's it. And this function is according to the circuit which we have seen in the theory lectures. So any doubts? Any doubts, ma'am?
No, no,
I
no,
think
no.
it is straightforward, right?
Yeah, it's
Yeah. Okay. Okay. Great. So then let us proceed now. Let us proceed with Shore's algorithm and try to learn that algorithm. Okay. So let us start with Shore's algorithm. And then we are going to see the Qiskit implementation later on in the evening. So Shore's algorithm for factoring. Order, it is also known as order or period finding. So Shore's algorithm for factoring, okay, which is also called order slash period finding. Okay, now let us start. So this algorithm, what it will do, it will be factoring integers in polynomial time. Okay, it will be factoring integers in polynomial time on a sufficiently sufficiently large quantum computer. Okay, sufficiently large quantum computer means basically it's trying to say that this algorithm works for the fault tolerant quantum computer, not our NISQ era. Okay, not the noisy ones, but this will be this algorithm is appropriate for the fault tolerant quantum computer. Okay, that is how this algorithm is, because remember it uses QPE, quantum phase estimation, as a subroutine, as a subpart. As I mentioned you yesterday, quantum phase estimation itself individually does not carry any significance. It has to be used in a some algorithms in some algorithm as a subpart, okay, as a subroutine. Then only it gives you the required result. So therefore, according to that concept, then you can see that this Shore's algorithm will require that fault tolerant quantum computer, a perfect qubit quantum computer where there is no noise. So if n let's say n is equal to p dot q. P dot q means p and q are multiplied, where p and q are prime and large. Okay, so remember that is the concept of Shore's algorithm, right? You can factor out primes for smaller numbers, but what happens if the number becomes very, very large? Let's say a 10 digit, 15 digit, or 20 digit number. Then you cannot do it manually, right? For small numbers, it's fine, like 1, 2 digit, it's fine to do. Okay, 2, 3 digits. But when it becomes even 5, 7, 8, 10, like very large 15 digit numbers, you cannot do it manually. It's impossible. So therefore, and this is where this algorithms comes into the picture. So therefore, classically, what is the complexity in classically? It is big O, right? Big O notation for complexity. Exponential, exponential what? C dot n 1 by 3. That means the cube root of n 1 by 3, and then log n. Okay, as you can see, 2 by 3. This complexity itself is very complex, right? Exponential, and also this is an exponential complexity. Okay, and n is the number of bits need to describe the factors, right? Because remember, like we are working with the binary logic, right? Because in classical computing and even in our whatever we are studying, it is all the part of digital quantum computing, right? We are all studying digital quantum computing. Why? Because that is more easy, and it is much more analogous to the classical ones which we have done, right? So that is why we are studying digital quantum computing. But this is a discrete one, but there is also another quantum computing which is the analog, which is the continuous one. Okay, that is not digital, but that is the continuous one. Okay, that field also exists, and that is also very good to be implemented using photonic circuits, the continuous. But photonics can also implement a discrete as well, so it's flexible. Now what happens? Shor's algorithm is little faster. So therefore, Shor's algorithm is a little faster than the ON cube. That means it is definitely better, and therefore it has more better factoring, only provided when the quantum computer is not noisy. So we use modular arithmetic in Shor's algorithm. Okay, we are using modular arithmetic in Shor's algorithm. We are going to see that. Okay, now let so now what is the Shor's algorithm? Let us see. Okay, now what will be Shor's algorithm? Let us see that here. Okay, Shor's algorithm. Let us write down the steps of Shor's algorithm, right? Then it will be easy. So what is the first step? First step is choose a random number A such that 1 a m. Okay, okay, m is some factor. Okay, capital M is a factor. Then second step will be if greatest common divisor GCD of A, and that M, the random number A, is smaller than M, is equal to 1. If the GCD of A comma M is equal to 1, Therefore, that means that a factor, because we are going to factor the value m. Okay, so let's say we are trying to factor 15. Okay, so what could be the primes? Okay, 15 is like into 5 into 3. 5 and 3 both are primes, right? So you can consider that m is equal to 15. You can take it as an example. Okay, and we are going to solve that also. So a factor of m is found. Okay, factor of m is found. If the GCD of A and M, that random number which you choose, let's say by chance you chose the random number to be 3, or let's say you chose the random number to be 5, then 5 comma 15 will be equal to 1, that GCD, and therefore that means indeed A is a factor of M, right? So you are able to break it. Rather, we have what we have to do, we have to break M into two parts, right? We have to break M into factors basically, and those factors should be prime. That is the condition. Okay, so therefore, as you can see, this algorithm has more closeness and more this. If you read the original paper by Shores, it is very closely related to mathematics and number theory, etc. Therefore, you need to have a lot of knowledge on number theory in order to innovate this kind of algorithm. Since Peter Shore had this knowledge, he was a mathematician. Therefore, he was able to find out factoring mechanism with the help of his algorithm which he devised like this, and then this could be implemented on a quantum computer. Now, third, find find order R of A mod M. Means A to the R is equal to 1 mod M. This should be satisfied. That is what it means. A mod M. Okay, find the order R. If order R means when a particular pattern repeats, like after a particular R, after a particular order, when it repeats. So if R is odd, okay, if R is odd, then you have to go back to step 1. Okay, but if R is even, then what will happen? But if R is even, then what will happen? Then let us see, then A to the R is equal to 1 mod M, and therefore A to the R, let us take the equation A to the power R, A to the R minus 1 is equal to 0 mod M, and we get, then we are able to have two kinds of factors, which is A R by 2 minus 1 and A R by 2 plus 1, which is 0 mod M. Now also assume, so for simplicity, assume that x AR by 2 is equal to x, just to write the equations in a simple way. So just let that AR by 2 is equal to x. Okay, just let this, then it will be easy. Then fifth step, check greatest common divisor of x minus 1 comma m and x plus 1 comma m. So both the GCTs needs to be calculated. If either of them are not 1, it means, in this case, if either of them are not 1, then factor of m has been found, and that is the success of the algorithm. We are going to take an example for this, so do not worry. We are going to see some steps. So if both if both are 1, both the GCTs come out to be 1, then repeat from step 1 with another with another a value. Okay, with another a value. So this is the Shor's algorithm. Okay, this is the short. Now we are going to see. Okay, now let us take an example. Okay, because this algorithm looks abstract, right? This is very abstract language. This is abstract mathematical language, right? Number theory is also very closely related to abstract mathematical language, right? So that is why. Hello, ma'am. Hello.
Oh, sorry, sir. I had net problem. The
No,
network
no,
completely unstable and it got disconnected.
no issues at all, ma'am. Ma'am, where you left actually? Could you please tell me, because I wrote the algorithm. So have you written the algorithm?
If I usually take screenshots, sir, so no problem.
Oh, okay, okay. So have you taken all these steps till
Yes,
sixth?
yes. Yes. Till
Okay,
5 I
okay.
took. Mm,
Or till five. Okay, sixth is this one. If both are one, then repeat from step one.
okay.
Okay. So then let us solve an example, because the algorithm's language is very abstract and it has been derived again from number theory, etc. So let us take an example. So let us solve a small example, and then we are going to see the circuit. So solving an example using Shor's algorithm. Okay, solving an example using Shor's algorithm, and we are going to factor. So factor m will be, factor m is equal to 15. Okay, as I told you, you can take an example. So let us take m is equal to 15. This should be simple, and even we are going to implement the circuit also for this. Okay, so now let us go, like, step by step. So let us say we pick a number. So pick a number, we pick a number randomly, right? That is the first step of the algorithm. Pick a number which is a. So let's try. Let's say that a is equal to 13. Okay, let's say just randomly something. Okay, and then we try to find the period. Okay, which is a to the power r, right? Okay, so period or order. Okay, same thing. Period of a to the r, that means 13 to the power r mod 15 we need to calculate. Okay, mod m, remember, a to the power r mod m, right? That is the value which was given in Shor's algorithm. So let us say that the r now will be what. So let us start with some values. So let's see if we define some values. X is equal to 0, 1, and 2, and let's say, like, 2, 3, basically some powers. Okay, we just need to put keep calculating the mod, and we need to see, and like so on you can go. Okay, and then let's say like like 13x mod 15. Let's try to find what the value comes. So when does it starts repeating? Okay, so here we get the value 1. This value will be 13 to the power 0 mod 15 will be 1. Then 13 to the power 1 mod 15 will be 13. Then 13 square mod 15 will become 4, and then here it will become 7. Then again it becomes 1, again it becomes 13, again it becomes 7. Now you can see the pattern. So 1 13 4 7, 1 13 4 7, 1 13 4 7. That means it is repeating after 4 steps, right? Can you see? After 4 steps, 4 steps. So after 4 steps it repeats, right? 1 13 4 7. And if you keep doing that, still again you are going to get 1 13 4 7, 1 13 4 7. Keep, you will keep on getting, right? So therefore is the r is the smallest number such that a to the r mod m is 1, and here a to the r mod m. So r will be equal to 4. A to the power r 1 mod m is equal to 4, and therefore r is equal to 4. So r is basically what? R is basically the period or the order after which this sequence repeat. 13 to the power x mod 15, right? 13 to the power value it repeats. So we have seen that it repeats after 4 steps. Therefore r is equal to 4. Therefore we found out r. So now what we are going to do, so now let us calculate. If you remember a r by 2, if you remember a x minus 1 x plus 1, remember that value. Okay, so now x is equal to a r by 2 mod m, which is equal to, what will be the value? Which is equal to 13 4 by 2 mod 15. And once you calculate that, you will get 4 mod 15, right? You get 4 mod 15. Now now remember, we calculated x plus 1 and x minus 1. Okay, so here we have taken x, to be equal to r here. So therefore what we are going to do, we are going to take the x plus 1 value. So x plus 1 value we take as 4 plus 1, and that becomes 5, and x minus 1 will be what? 4 minus 1, which is equal to 3. So we are going to use these two values. Okay, therefore GCD of x plus 1 comma m is equal to GCD of 5 comma 15, which you get to be 5. Okay, and then GCD of x minus 1 comma m is equal to GCD of 3 comma 15, which is equal to 3. Once you get these GCDs, therefore you can see, according to the algorithm, none of them are 1. Remember, in the algorithm it said check GCD of x plus 1 x minus x plus 1 comma m, x minus 1 comma m. If either of them are not 1, therefore the factors of m has been found, and therefore that is a success, as you can see. So therefore p comma q, the factors, prime factors, are indeed 5 comma 3, because either of them are not equal to 1, right? Either of them is not equal to 1. Here it is written. Fifth step, check GCD. If either of them are not 1, then factor of m has been found. That is the success. Therefore, the algorithm terminates here. Now, what will be the quantum circuit for this? Let us see. Okay, what will be the quantum circuit? Okay, of Shor's algorithm. So let us do it on the next step. Let us do it here. Quantum circuit, because remember we have to solve this problem using quantum circuit, right? Quantum circuit for Shor's algorithm, where we are going to take m is equal to 15 and a is equal to 13. Okay, remember this thing, a is equal to 13. Now let us start drawing the circuit. So we will have two registers. Okay, first register, second register. So let's say we initialize them, and remember the formula also, f a comma m. Okay, this is the function which is implemented. Remember, a x mod m. Okay, this is the function which is implemented by the Shor's algorithm. Okay, so let us start drawing. So first we start with Hadamard gate. So here we have Hadamard gates. Let us start with 4 qubits and Hadamard gate, and each of them are basically 0. Okay, each of them are this. Let's say this is x. Okay, x is the first register, w is the second register. Okay, so let's say each of them are initialized to 0, as we already wrote tensor 4. Okay, tensor 4, right? All are 0. And then also we have the second register. Okay, also we have the second register. This is the second register. Let us call it w, and that is also initialized with all zeros. Okay, tensor 4. Okay, and now look here. Okay, what is, look at this circuit. This is the function. Okay, and we are going to take the measurement of this circuit beforehand itself. If you recall now that this circuit resembles very much that of the Simon's algorithm. If you remember, Simon's algorithm can also be used for period finding. Okay, but not very efficient. Okay, but it can be used. And if you recall, only in Simon's algorithm we have seen a measurement which was taken before. Okay, for the second register to collapse the second register qubits, if you recall. So this also has the same structure as the Simon's algorithm. You should definitely go back to Simon's algorithm and check it again. This resembles very much same to the Simon's. And if you see in Simon's algorithm, in the first register we apply Hadamard gate after applying the unitary. The only difference between Simon's and Shor's, and this is the beautiful fact you will see, the only difference between Simon's algorithm and Shor's algorithm is that in Shor's we are applying QFT inverse, QFT dagger, but in Simon's algorithm we applied Hadamard instead. Okay, so therefore only application of Hadamard was not very efficient in finding the period if you use it for period finding, but in Shor's you apply the QFT dagger and it makes the process much more efficient. So that's the only difference also you can see. And this is f a comma m, which I defined above, right? A to the x mod m. So this is what the function is implemented. and then this second register is already collapsed, so therefore this keeps going. Okay, this keeps going, and then we are going to apply QFT dagger. That means the inverse QFT. Okay, QFT dagger, and we are going to take measurement. Simple. That's it. That is the circuit for Shor's algorithm. Okay, that is the circuit for Shor's algorithm, and you will get output. Okay, and therefore, since you have the circuit now here, and it is also not very hard, if you see, I mean, this is this is the same, similar as Simon. If you remember, also in Simon's algorithm, we first time encountered the notion of having multiple qubits in the second register. Remember, this is the first register, and this is the second REG register. Okay, and only inside, if you remember, after Bernstein Vazirani, you learned Simon, and only there you saw this concept of having multiple qubits in the second register. So this circuit is similar to Simon's. I strongly recommend go back to Simon's algorithm circuit and compare it, and you will see that this is the same circuit. The only difference is that the Hadamard is not applied after the unitary, but QFT dagger is applied. Okay, so that's how makes the Shor's algorithm circuit different. Okay, and also we can now mark it. Okay, we can mark the label. So for example, let's say this is the point and this is the 0 point. Okay, you start with 0, and then this will be 1 point for circuit analysis. This is 1. Okay, then this is 2, and even for Simons also we did a similar kind of analysis, right? So therefore it should happen very similar to sine. This is 4, and then this is the fifth one, right? So this is the thing you should be aware of. And now, as you can see, this unitary, so this unitary is what? This unitary is nothing but ket x. Okay, I'm just writing in general form, a ket w. Okay, just name them, where this is getting translated to ket x and ket w XORed with f of x a comma m. That's it. That is the function of the unitary article. I mean, you are already aware of this, right? I mean, this kind of formalism is there in Deutsch Jodsa, Bernstein Vazirani, right? All the functions are implemented in this format, right? So that is the formula. Now let us start solving. So let us start with the step 0. Okay, step 0. In step 0, you have ket 0, which is this is x. Okay, remember this is x, tensored 4, and also you have ket 0, which is your w register, tensored with 4. Okay, so x and w. Then in step 1, what you are going to do, you are going to make Hadamard very similar to Simon's. Okay, so in step 1, Hadamard will be applied to. So Hadamard tensored 4 is applied to zeros. Okay, all the zeros, and the second qubit is left untouched. Okay, second qubit, that means the w register. The w register is left untouched. X register, in the x register we are applying the Hadamard, and then once we apply to 4 qubits of Hadamard, okay, then you are going to achieve the superposition of all the 16 states, right? Because 4 qubits is what? 2 to the 4, right? Which will be 16, right? So that is why you are going to get all, and I'm not going to write all the 16, so of course, because that is not the thing here. I'm going to write them later on actually. So let us just write them in short. Okay, so you get this like get 0, okay, 4, then get 1, and so on. Okay, get 2 plus so on up to 15, right? Because there are 16 total, right? So 0 to 15. We write it like this, and this is W register which is going on. So this X register with X register is now in superposition. Now step 2. Step 2. So now what we can do now, since we know in step 2 we have to apply, remember we have applied the oracle, right? And oracle formula I just now gave you here. Okay, what is the formula? W XORed with, okay, here if you see my cursor, W XORed with fx a comma m, and fx I have already defined. Okay, I have already defined fx, so therefore we should apply that now. Okay, we should try to apply that step 2. Okay, so how are you going to apply? So let us see. Let us see now. Look at this step very carefully. Okay, this is important. 1 by 4 get 0 4. Okay, that means get x and then get W XORed with fx, right? So W XORed, so whatever W was there, W are all zeros. Okay, so therefore W, look at this step carefully, W 0 XORed with fx a comma m. What is fx a comma m? A to the x mod m, right? A to the x, what is a? A is 13. I have already defined. M is 15, a is 13, right? So there a to the x 13 to the power 0. Okay, because x is 0 now. Okay, x is 0, right? This is what? This is x. W, okay, W XORed with, okay, let me write it for the first time, since a to the x, okay, remember the value of a is 13 always, x, okay, a to the x mod 15. Okay, this is how we are writing. Okay, got, I hope that you got it. Okay, we are using that formula basically. Okay, x W XORed with fx, right? A comma m. And similarly, this can also be now done for what? Now x will be what? X will be ket 0, then x will be ket 1, right? It will go on for all the 15 states, right? So therefore this time it will be, again W is 0 only, so 0 XORed with, this time what? It will be 13 to the power 1, right? 13 to the power 1, because it is a to the power x, right? A to the power x mod m, remember. Okay, so therefore it will be, mod m remains same, mod 15. Okay, and so on, right? It will go on, right? It will go up to get, like it will go up to like basically the last step. Okay, okay, what will be the last step? You can note down the last step. Okay, so I mean it is familiar, but okay, anyways I will just write it down. Just okay, get 15, right? And then 0 XORed with 13 to the power 15, remember a to the power x, and then mod 15. Okay, so that is how it will go on. Okay, so this step is easy. We have just applied the formula. You know the formula. Okay, the formula is very similar to that which you have learned before. That XOR operation, that unitary implements that XOR operation. We saw it first time in the Deutsch algorithm, right? Where we were seeing Y XORed with fx. Do you recall? Where Y was the second register single qubit, and we said Y XOR fx. So very similar thing. Okay, here we have W. The names and variables have changed, but the concept has remained the same. Okay, that is why learning concept is important. So the name variable can change, but the concept will not change. Concept remains the same, right? So therefore now equal to, now let us write it down. Okay, 1 by 4. Okay, ket 0 4, and then what we are going to have is this value. So we are going to have 13 to the power 0 mod. So basically we solve the XOR, and anything XORed with 0 is that value itself, as we know. So therefore we get this value, and this is indeed 13 to the power 0 mod 15 is what? This is 1, right? This is 1. Then plus 1 4, then again 13 to the power 1 mod 15. Okay, this is what? This value is what? 13, right? Then plus 2, and again 13 square mod 15. Okay, this will be what? This is 4. Okay, remember the pattern. 11347, right? 11347. Do you remember the pattern which we have solved previously in the example? That is the pattern, remember. So now we can write accordingly. Okay, 11347. Now I'm going to write all the terms, and you are also going to do the same. The reason, because this will give you more clarity of what is happening. So ket 0 4, then ket 1 4 plus ket 1 4, and then ket 13, okay, plus ket 2 4, and then 4, and plus ket 3. Okay, remember, first register X, second register W. First register X, then second register W. Remember, in that format we are proceeding. Okay, 7. And now after this step we are going to collapse it, right? We are going to collapse the W register, right? How? By taking measurement, right? As we have seen in the quantum circuit, we are going to take measurement. Very similar to Simon's algorithm. Remember, we have studied Simon's already. Okay, plus then get 4 4, and then again it will start. So now you can write it very easily, right? So this remains same. Okay, so you can see what remains same and what is the difference, and this is 7. Okay, plus, and then get, this will become 8, right? Then 9, then 10, right? And then 11, right? So these are all those terms which I was not writing earlier. Now I am writing them all together. Okay, this is the, oh, these are all those terms. Okay, and this is going to be closed here. So this is the last one. Okay, okay, 12. Okay, this is 13, and then this is 14, and this is what? This is 15, right? It would go up to 15, right? We have seen. Okay, it goes up to 15, right? But the W register, as you can see, it remains the same, 11347, right? 11347. Remember? So now step 3. Now we will collapse the W register. Okay, we will take the measurement. So step 3 is measure the get W register, which stores all these repeated values, 11347, 11347, right? It stores all these values, right? Say, and let's say, and remember, measurement collapses to some particular value, right? So let us assume, say, like, it can be other value as well. So, but just as an example, let's say we measure ket W, like, because since ket W can take only 4 states, right? What are those 4 states? 11347, right? Only that ket W can take. Apart from that, there is nothing else, right? As it is very obvious from the that's why I wrote all the terms, right? That was the reason to write all the terms, so that you can observe ket W. Remember, the observation is for ket W because we are collapsing that. So remember, ket X, ket W. Ket W is only taking the 11347. So therefore, out of those 4, any one of them is going to be measured. Okay, any one of them is going to be collapsed. So let's say we measure kW to be, let's say it collapses to this state. Let's say 7. You can take any other example also. Okay, it can be 1, it can be 13, it can be 4. Okay, but let's say it's 7. Okay, you can take 13 also, it's fine. Okay, anyways, it is collapsed now after taking measurement, and we are only now going to deal with the first register. Okay, so therefore at that time you will have ket x, ket w is equal to half. You are going to have what? You are going to have, since we got 7, okay, therefore we are going to see that the terms with 7 are going to be left in the superposition, right? That is what is going to happen because we have collapsed the second one. Okay, and let's say it collapsed to 7. So what are the terms where we have 7? Look at this fourth column: 3, 7, 11, 15, right? Therefore those are the terms which are going to be left in the superposition. So therefore 3, okay, the superposition becomes 7, 11, and 15. These are the things which are left once we collapse it. Okay, once it is collapsed, because 7, we collapsed to 7. Let's say we measured that. Therefore, all the terms associated with that will be left in superposition, and all the other terms will no longer be present. So therefore, by measuring the second register, we basically reduced our calculation, and now on top of that, now we are going to apply step 4, which is applying the QFT. Okay, therefore now on those terms which we are left in step 3, we are going to apply the QFT dagger. Okay, inverse QFT. So apply QFT dagger on the ket x register. Okay, on the ket x register, right? Because now ket w is gone, right? So what is the formula of QFT dagger? You have already studied this, but I am going to mention it. Okay, because since we are going to use it now, okay, it converts x tilde, which is what? X tilde is what? Fourier basis, right? It converts from Fourier basis to computational basis. That means it will convert to ket x, right? And what will be the formula? 1 by under root n summation y is equal to 0 to n minus 1, right? That is what you have studied. And e to the power minus, right? In the quantum Fourier transform, normally when you go from computational to Fourier basis, it is e to the power is positive, right? And in this case, it is negative. There is a sign change difference, right? In the formula, as Mohammad Amir might have discussed with you, x, y divided by n and get y. Okay. This is the formula for QFT dagger, and now we are going to apply QFT dagger to each of these terms. Look at this, each of these terms: ket 3, ket 7, ket 11, ket 15, right? We are going to apply to each of these terms, and then we are going to write them together basically. Okay, so let us do that. Okay, let us do that one by one. We are just going to apply the formula. So uh will not do, like, nothing very big thing, but just applying. So QFT dagger will be applied to 3. Okay, and therefore what we are going to get is 1 upon under root 16 summation y is equal to 0 to n minus 1 e to the power minus 2 pi I 3 y divided by 16 and get y. Okay, just we are just individually calculating all the terms. Okay, Similarly, it's very easy. So now you can remember X is the get X register, right? So therefore 2 pi I 3y. It was XY in the formula, if you can see. We replace the X with 3. Similarly, we will now replace it with other values. So 3, and then let's say we also apply to 7, okay? Which is again, so again, now you can write it yourself. This is very easy. Y is equal to 0 and n minus 1, and then we are going to sum them together. First, let us write down the terms individually. 2 pi I 7y divided by 16 get y, okay? Then UFT applied to 11, right? That was 11. 3, 7, 11, 15, right? Those are the states. 1 by 16, and then y is equal to 0 to n minus 1 e to the power minus 2 pi I 11y divided by 16, and finally QFT applied to 15, 1 upon this summation y is equal to 0 to n minus 1 e to the power minus 2 pi I 15 y divided by 16 and y. And now let us write them together, okay? So basically QFT dagger has been applied to X register, okay? And we are going to get 1 by 8. So let us take the summation outside, because summation is same for everyone. So, and the summation will go from y is equal to 0 to 15. And let us just sum all those e to the power terms together, okay? So therefore we are going to get e to the power minus I 3 pi by 8y plus e to the power minus I 7 pi by 8y, okay? So let us do, and now y, then this is y, okay? This is 8y, and then plus e to the power minus I 11 pi by 8y plus final term e to the power minus I 10 pi by 8y and close summation, and also get y is there, okay? So once you are able to calculate these values, e to the power values, all these values, once you calculate, then you are going to get this result 1 by 8, and also add the summation as well, because remember y will be going from 0 to 15, so therefore you have to calculate according to that on each of the, because remember summation is on each term. So once you open up the summation, y will be going from 0 to 15 for each of these terms, right? Because remember y will go from 0 to 15 and you have to calculate. So once you do all those, that's a large calculation, right? So that can be done using a computer. It's not this is not something which needs to be done by hand, okay? But once you do that large calculation, then you are going to get these states, okay? Once you do, then you are going to be left with these states. Look at these states: get 4 minus 4 get 8 and minus 4i 12. So basically you are going to left with these states. So get y will be taking these states and the coefficients, so many of the terms will be cancelling out as well. That is why we will be only left with these terms, and this is not something to be done with hand, okay? This needs to be done with a computer. Whenever you have computations like this, it's better to make a for loop and do the calculations there. Now step 5, we will be measuring the X register, right? So we measure the get X register, which is 0, 4, 8, 12, right? It has only four states, 0, 4, 8, and 12. If you can see, with equal probability, with equal probability. Okay, you measure these. Okay, now what will happen now? Now we are going to apply the Shor's algorithm. Okay, now according to Shor's algorithm, also measurement results measurement results peak near Jn by R for some integer j which belongs to z. Okay, so let us take an example what this means. So eg, let's say eg, we measure, let's say we measure uh let's say we measure ket 4. Okay, you can take other value also. There are four values, 0, 4, 8, 12, right? Let us say that we measure ket 4. Let's just say an example. Okay, that means j n by r. Okay, that means 16 by r is equal to 4, right? That is what it means. J 16 by r is equal to 4, right? Because the measurement results, what are we going to measure? We are going to either measure 0, 4, 8, 12, and the jn by r, the measurement result should peak near jn by r. Therefore jn by r should become equal to 4, right? And n is equal to 16. Why 2 to the 4? There are 4 qubits, right? We have taken only 4 qubits in the first register, right? So that's why 2 to the 4, 16. So that means it becomes equal to that. Therefore this becomes true only if j is equal to 1 and r is equal to 4. Okay, so this equation will be satisfied, this equation satisfied when j will be equal to 1 and r will be equal to 4. So therefore now we are going to try with all the values. Okay, r is equal to 0 we cannot try, because remember, if we put r is equal to 0 in the denominator, then anything upon 0 will become infinity, right? Then it becomes invalid, right? So therefore r is equal to 0, definitely we have to skip it. But the other values remain, 4, 8, 12. Now we are going to try with those. So let us try for, so remember, this is the, after applying Shor's algorithm, this is the post calculation steps. Okay, so that means that Shor's algorithm gave you some measurement values, and based on that now you are going to apply. Okay, okay, so let us do, so let us take, so for r is equal to 4, remember r is equal to 4 is even. Okay, is r is equal to 4 is even. So therefore remember, we have calculated x is ar by 2 mod m. We know a, which is 13, we already defined it. R by 2, this is currently 4 by 2, mod 15, which is equal to 4. Therefore x plus 1, again x plus 1, x comes out to be 4, right? So x plus 1 is equal to 5, x minus 1 is equal to 3. GCD, calculate GCD. The steps are very similar which we saw when we were calculating that example. Then x minus 1 comma m, which is equal to GCD of 5, 15, which is 5, then GCD of 3 comma 15, which is 3. Okay, 5, 3 we received. Okay, let us try another r is equal to 8, right? We still have 8, 12 left, right? So let us see that. So basically those are r values which you received from the Shor's algorithm. Now you're going to see which one matches. So r, for r is equal to 8, that means j 16 by r is equal to 8, which means This will be possible when j is equal to 1 and r is equal to 2, or j is equal to 2 or r is equal to 4. Okay. So since r is equal to 4, we have already tried, right? R is equal to 4, we already tried above, but we have not tried this one. Not tried this one. R is equal to 2, we have not tried. So therefore, x13, 2 by 2, r by 2, right? So 2 by 2, mod 15, mod 15, okay, which gives 2. So therefore, x plus 1 is equal to 3 and x minus 1 is equal to 1, right? Again, same GCD of 3 comma 15, which is equal to 3, and again calculate GCD. 1 comma 15 is equal to 1. Okay, therefore, as you can see, it gives only the partial solution. As you can see, for r is equal to 8, we are only able to see a partial solution. Okay, partial solution. But for r is equal to 4, we are able to get a full solution. If you see, when you multiply, solution means when you multiply those two values, you should get 15, right? That is the solution. But here you are able to get one of the factors, 3, but not the other one. The other one is 1, right? Therefore, this is a partial solution. Okay, so you can see all, like, how the Shor's algorithm, post processing analysis, you are able to get the result. Then r is equal to 12. The same thing you have to try. J16 divided by r, okay, is equal to 12, and that means that r should be equal to 4 and j is equal to 3. So r is equal to 4, we have already tried. So therefore, what is the conclusion? A quantum computer suggested Ket 4, Ket 8, and Ket 12. Okay, Ket 12, Ket 12 works. Okay, and we are able to extract factors. However, if Ket 0, try again. Okay, so quantum computer was indeed able to give you some options for r is what? The period or the order, right? And we are also going to find, we are also finding period or the order using Shor's algorithm, right? And then with the help of that, we are able to find the factors. So therefore, both the work we are doing, we are able to find some order or period. From that, we are applying the Shor's algorithm, the last steps, like the steps fifth. Okay, step 5, we are applying it to check the GCD, and if it is, if and we check whether it indeed it gives, at what period it gives the full solution, not the partial solution. So if you see, for r is equal to 12, we get r is equal to 4. When you solve that, j16 by r is equal to 12. That can only happen where r is equal to 4 and j is equal to 3. Okay, so that is, this is what like proves that for both the factors, r is equal to, for the 4 and 12, we are able to receive a full solution. Okay, so only for r is equal to 8, that is the partial solution, therefore we can ignore that, and therefore r is equal to 4, that gives us the, it gives us the full solution, right? Because we know that j16 by r is equal to 4, and that is true only when r is equal to 4. Similarly, for j16 by r is equal to 12, we know that r is equal to 4, and we have already calculated that. Already calculated, right? Now, since we are already calculated, we are not doing it again, right? I mean, why should we do it when we have already calculated and we know? Therefore, both those factors, 4 and 12, those values, 4 and 12, they give the full solution. Okay, so therefore this is also full solution. So only one factor gave the partial solution, but also observe that it gave some solution. Okay, it gave you partial, not full, but at least it gave you something, remember. Therefore you can try the other factors like 0, 4, 8, 12. Okay, let's say you first tried with 8 and it gives you partial solution, then you see that okay, multiplying those two does not get to m is equal to 15, right? Therefore you can take out another factor and again calculate this j16 by r and so on, and calculate the gcd, etc., and try to, and then you will try to find the another factor, right? So therefore you can see that the factors, the orders which are suggested by the Shor's algorithm are accurate, and once you do the appropriate post processing, appropriate analysis, where GCD and etc., these stuff can be done using Python. No one needs to do them manually. The reason, because the goal of Shor's algorithm is to factor larger numbers, not smaller. This is an example case, that's why we have taken smaller. Of course we cannot take a very large 10-digit number and try to factorize it, right? Even if we do, we will get extremely noisy results in today's quantum computers, therefore we cannot do that. Okay, so this is the Shor's algorithm, and the Shor's algorithm circuit, the implementation. So basically the implementation is similar to QPE, quantum phase estimation, right? So quickly I will just mention the basis circuit for that, which is known as the modular exponentiation circuit. Okay, that is the your, this is how your u of fam, right? That u of fam you saw, right? U of fam, where is u of fam? Here, this one, u of fam. This is how the u of fam is implemented. You might have this query how that u of fam is implemented, right? So this is how it is implemented, algorithm. Okay, now note that x is equal to x1, x2, x3, so on up to xn, which again in binary you can write 2 to n minus 1 x1 plus 2 to the n minus 2 x2 and so on, plus 2 to the 0 xn. Okay, so therefore f of a comma n or a comma m, anything which you like, those are just variable names. So it's your wish, whatever you can take in that. So mod n or mod m, I mean anything which you like. Okay, and from that, therefore what we see, therefore we are able to see that we will have a x. X is what? 2 to the n minus 1 x1 plus 2 to the n minus 2 x2, which we wrote it. Okay, plus 2 to the n minus 3 x3 and so on, say up to 2 to the 0 x, right? So this is, and mod n is also there. Okay, we are just expanding, that is it. So we're not doing anything, just expanding. And therefore now we can write them separately. So it will be a2 to the n minus 1 x1, then a2 to the n minus 2 x2, and so on up to a2 to the 0 x n mod n. Okay, and therefore where we are able to apply the, as you can see, we have 2 to the n minus 1, 2 to the n minus 2, 2 to the 0, right? And we are already familiar that this kind of structure we have seen in u2 to the n minus 1, u2 to the n minus 2, right, with control phasing. Just now we saw quantum phase estimation, right? So therefore a rough circuit, a general circuit for the Shor's algorithm is given as follows, where you have all the Hadamards here, Hadamard tensored n, where all these start with 0, tensored n. Okay, and there then we have these values, and from each of those we apply the unitaries, right? U 2 to the 0. We saw that, right? QPE circuit. Basically the QPE circuit, okay? Second, then second one is what? Second is U 2 to the 1, and then, like, let us extend this a little bit more, so that we have more, and then this is third one. Okay, this is just a general circuit. It will go on U 2 to the n minus 2 and 2 to the n minus 1. It will go till 2 to the n minus 1 here. This one, fourth one. Okay, U 2 to the n minus 1. Okay, and also you have the second register. Okay, so this is like your X, this is like your like, your W, basically, which again started from 0, 10 certain, and like that. Okay. And then finally you have the QFT inverse, right? QFT dagger, and you take the measurement, and that's it. And that is how the circuit of, this is what, this circuit. Okay, if you see, this is the circuit. Okay, this is the circuit of U F A comma N. Okay, this is how it is implemented with, and this can be implemented with controlled phase gates, which you saw, basically the QPE circuit. Okay, so therefore that concludes the Shor's algorithm. So any doubts in this? Hello, ma'am.
Yes, sir. Thank you.
Is this good, ma'am? No doubts, right?
Yeah, yeah. No doubts, no doubts.
This is straightforward only. We have just applied a few formula and followed the steps, right? So
Yeah.
I think it's straightforward only.
Yes, sir.
Okay, okay, great. So let us conclude here, and then in the evening I will just take a few minutes and explain the Qiskit code for Shor's algorithm, and with that Shor's algorithm will conclude. And next week Grover's search will be taken by Muhammad Amir.
Oh,
And
great.
next week Saturday, it might be a little bit more longer class than 1 hour. It might go up to 1.5 hours as well, because
Okay.
he's going to complete Grover's algorithm in Saturday itself.
Okay.
Yeah.
Okay. Yeah.